Hi, and welcome to my talk on React Native. I'm going to be diving into the platform and sharing what it's like from the perspective of an SDK. My name is Ben, I'm from the UK, as you might better tell from my accent, and I work at Bugsnag as a platforms engineer. This talk isn't going to be hugely about what Bugsnag is or about error handling in general, but rather the things we've learned about React Native while building and maintaining Bugsnag's SDK for the platform. But I will tell you about the company and our product just because it's useful to have that context. Bugsnag is an application stability management platform, and essentially we do two things. The first is error reporting, so that's detecting things like crashes, exceptions, and errors, and giving you the tools to reproduce those errors in order to work out the root cause. And the second thing is stability monitoring, so using those errors and also recording the number of sessions your app has, we calculate a stability score, which is based on the ratio of crashes to crash-free sessions. And that gives an overview of the stability of your app. This will give you an idea of whether to concentrate on fixing all the bugs you just rolled out, or whether it's okay to carry on working on new features. And if you use Bugsnag, you're in good company. Here are some of our customers. Now, I said I was a platforms engineer. What does that mean? To explain, I'll show you what engineering broadly looks like at Bugsnag. So we have our dashboard, which is a web app, and this is where we show you your errors, along with all the stat traces, telemetry, context, and metadata. And that speaks to our API to load its data and do various operations. The API in turn interacts with a whole bunch of services that we generally call the pipeline. So engineers on our dashboard, website, and pipeline teams work on this stuff, and the infrastructure here is probably fairly familiar to those of you who work on web or SaaS apps. And so the software we deploy here, we remain in quite close control of it. We know what OS it runs on, we control its dependencies, and the software that it coexists with. And that means we're able to do things like monitor it, notice problems, investigate the data in the databases, and quickly roll out fixes if we notice any problems. But how do we get the errors in there in the first place? Well, that's the job of my team, Platforms. So we're responsible for writing and maintaining our error reporting SDKs. You'll hear me refer to these as notifiers. We provide these for people to integrate into their applications. So for any platform we support, JavaScript, Android, iOS, React Native, etc., we provide an SDK that will automatically capture errors and send them to our API. And these are all developed in the open, by the way. They're on our GitHub, so you can vet them and see exactly what you'd be trusting to run inside of your app. And so even before we get into the specifics of React Native, working on these SDKs is a really interesting way in which to write software. Unlike the dashboard, API, and pipeline teams, at Bugsnag the platforms team is very far removed from where our software is deployed, and that poses all sorts of problems. So we don't run our software, we hand it off to you as our customer, and you run it. So as the author of Bugsnag.js, for example, our JavaScript notifier, I don't get to choose what bundler you use, whether you modify a bunch of built-in globals in the browser, whether you support some ancient browsers like IE8, or whether you choose to run it alongside some other error tracking or analytics tool that causes conflicts. I essentially have to anticipate the most hostile of environments, and not only that, but since I'm not in control of deploying that software, you are. If I fix a bug or create a new feature, it's not straightforward to roll out an update. I can publish that, but then I need to wait for you to update your version of your notifier. And then, particularly for mobile apps, I need to wait for your end users to get the new version of the app too. And this all means that a bad version could be running in production for a long time, so we want to avoid shipping that in the first place. So while ensuring the SDK works in these hostile environments, we also have to be really careful about causing problems ourselves. We're an application stability tool, so imagine importing Bugsnag into your application to detect crashes, only to find out Bugsnag causes a crash. And not only do we have it tough in terms of the situations our code might end up running in, not only do we hold ourselves to a really high standard of stability and resilience, we also strive to be a good citizen. Importing Bugsnag shouldn't break or change any part of the platform that your or other third-party code makes reasonable assumptions about. And what this means for my team then is that we have to be incredibly risk-averse and do very thorough testing. So on to React Native, the first thing I want to talk about is abstractions. In software, we talk a lot about abstractions. We deal with them all the time. When we set out to write an application, we don't start off with the list of operations our CPU chipset supports and start from there, right? We use programming languages, markup, frameworks, and APIs. So what is an abstraction? The way I understand it is as a container for some complexity. It hides that complexity from you, so you don't have to care about the details or even understand it, and to a degree it's a black box. But just hiding it from you makes it useless, so as well as hiding it, it has to provide something to interface with. So for me, an abstraction is two things. It's a container and an interface. And a way that people often think of React Native is as an abstraction over native mobile platforms. It contains libraries, native code, glue, and logic, all which serve the purpose of running a JavaScript application on native development platforms. So into the container goes the complexity of native mobile development, and on top is interface, its API, CLI, and other tooling. So is it an abstraction? Well, yes, but is it a good one? An attribute, usually a critical one, of abstractions is leakiness. For an abstraction to be leaky means that it doesn't do a good enough job of hiding the internal details from you, and so therefore, as well as dealing with just the interface of the abstraction, you have to deal with the complexity of the internals too. In the worst case, this means that you need to understand more than you did before attempting to abstract away that complexity. The problem with React Native is that when you choose it over native mobile development, not only do you need to know the JavaScript and web application stack, you also need to know the native platforms too. So whilst React Native is careful not to sell itself as this, lots of the discussion and excitement around it has been about lowering the barrier to entry for mobile development. And whilst it does make it easier for JavaScript engineers to participate in mobile development, some of that nuance is inevitably lost. So ultimately we end up with a lot of people using React Native who very quickly find themselves out of their depth, facing obscure build failures in Xcode or Android Studio. This stems from a lack of familiarity of those platforms, but those developers were given almost a false sense of confidence in React Native because it felt familiar. So if you want an abstraction over native mobile development platforms without the leaks, my advice is this: use Expo. I'm sure many of you will have heard of Expo, and in fact it's already so widely used and does such a good job that it's now recommended in the React Native docs as the default way to build a React Native app. Expo not only hides the native layers from you, and so you only have to write in JavaScript, you in fact can't even write native code even if you wanted to. You don't even need to install Xcode or Android Studio on your laptop to build a mobile app. So one way of looking at abstractions with holes in is leaky, but there's an alternative, and that's as an escape hatch. If you do end up needing to do something in Expo in native code that they don't support with their APIs, then you have to eject and you're out of the cozy walled garden and you're out in the wild again. It's an escape hatch but with no return. React Native, on the other hand, allows you to escape from the sandbox JavaScript container easily, meaning you have the full flexibility and power of the native platform whenever you need it. The downside of this, that I already mentioned, is that you can't really avoid that native complexity. So while you can write the majority of your application in JavaScript, you still need familiarity with Android and iOS development, even if that's only to deal with packaging up and publishing your app. Ultimately, it's a trade-off which may differ depending on your situation. Are you a team of JavaScript engineers that needs to hit the ground running with a mobile app? Then you should probably use Expo. Does your team contain mostly JavaScript engineers but some with some good native experience? Then you should probably use React Native. And if you're a team of mostly mobile engineers, then maybe you should just write native apps. As the maintainer for Bugsnag for React Native, but someone whose background is predominantly working with JavaScript, thankfully alongside me we have domain experts in Android and Cocoa development, and we all collaborate on our React Native notifier. That broad level of expertise across the board is absolutely essential, and I simply wouldn't be able to do a good enough job as a JavaScript engineer alone. So in terms of error handling and crash reporting, with Expo, native crashes can happen, but ultimately they will never be your fault, and you'll never be able to action them even if they were reported, because you can't tweak the native code, so you only really care about JavaScript errors. But with React Native, on the other hand, it's a different story, and that leads me on to my next topic. When an application starts, there's a lot that can happen before a single line of your JavaScript code will run. If you're writing a React Native app, specifically not Expo, you're in control of the native layer, and so crashes before that point could be your fault. Now, how do we ensure we capture every error? In a bit more detail, this is the sequence in which a React Native app starts up. On the left-hand side here, the user presses the app icon. The OS allocates some resources and starts the main process of your app. Now this is your process, which includes the native runtime and your native application entry point. So right away there's some code that you or your team wrote which could potentially crash. Then the React Native runtime loads, starts a JavaScript virtual machine, loads your JavaScript bundle from the disk, before finally executing the JavaScript app and rendering your first component. So the crux is that you can introduce errors at any point after the dashed line on the left-hand side there, and you'll really want to know about them. Arguably, crashes during startup are the most impactful to your users and bad for your app in terms of usability and reputation. In the past, since React Native is predominantly a JavaScript-based platform and the third-party ecosystem is oriented around consuming modules from NPM, the JavaScript package manager, and simply to allow ease of use, the default way to configure Bugsnag was to do it in the JavaScript layer. But that means that any crashes happening before the dash line on the right-hand side, these potentially really important crashes, well, they wouldn't be reported by default. So we've re-engineered our notifier to ensure that we capture every error by default. And we've done that by making sure that Bugsnag can start incrementally, first in the native layer, and subsequently adding JavaScript reporting once that layer gets up and running. So by ensuring that we get the native reporting started as early as possible, we can be watching for errors at the earliest possible moment, meaning that we're that bit closer to capturing every error. So we've got our notifier up and running, first in the native layer and then later in the JavaScript layer. We need to synchronize state and send data between the two. So how do they talk to one another? This is an overview of React Native's architecture. On the left, we have the JavaScript virtual machine, which is running your JavaScript and rendering your components. On the right, we have some native threads, which are Cocoa or JVM, depending on the platform. And what sits between the JavaScript and native layers of React Native is a thing referred to as the bridge. Now, the bridge is an asynchronous batch queue, which allows serialized data in JSON format to be passed to either side. So both layers can add to and consume from this queue, but the API is different depending on what you're trying to send where. So if we look at the various ways in which we might want to transfer data, I've highlighted which APIs you can use to do so. If you want to push data from JavaScript to native, you can write a native module. A module in native code that you annotate to tell React Native, I want this interface to be exposed to JavaScript. And similarly, if you want to pull data from native to JavaScript, you also use native modules. If you want to push data from native to JS, then you send an event from native code and then you listen for it in JavaScript. And if you want to pull data from JS to native, well, you're a little bit stuck. If you really need to do this, then you'd need to emit an event that denotes I want this data and have the JavaScript layer respond to that event by calling into a native method. But given how laborious and error prone that sounds, I would avoid designing anything around that pattern if possible. So this might be a bit of a recap for some of you if you're doing a lot of React Native development already, but to catch everybody up, I'll go and show this in a little bit more detail. Now here's what a native module implementation looks like. On the left, we have Objective-C, and on the right, Java. The macros and annotations instruct React Native to instantiate a singleton of this class, so one instance for the entire runtime of your app, and then exposes it to JavaScript. And the snippet at the bottom there shows how we access and interact with it from JavaScript. So that was quite a boring example that neither sent nor returned any data. And here's how to transfer data, just shown in Java for brevity. And you don't often hear the words Java and brevity in the same sentence, do you? We have straightforward argument passing for any simple types that serialize to JSON, so numbers, booleans, strings, maps, and arrays. And here the setName method simply takes a string. The getName method for retrieving data from JavaScript is a little more interesting, and it takes a promise. So remember that the bridge is asynchronous. So all bridged methods have a void return type, and they should return their data via a promise. And there is an exception to this, and I will tell you that we do use it once in our code base out of necessity. There is an annotation that you can use to mark a method as synchronous. You should only use this when absolutely necessary, as it will block any other execution. And so here's how we'd call those methods from JavaScript. SetName is pretty straightforward, as you'd expect, but see how in getName we don't actually pass the promise in as an argument. That's done for us by React Native, and the promise becomes the return type. So we can use the nice modern JavaScript await syntax to asynchronously resolve this value. Events are a little more tricky. The API is different for each platform, and here I'm just showing a taster of how to do it in Cocoa. There's more boilerplate to add when you do this for real. So here, ahead of time, we have to tell the emitter what kind of events we'll be emitting, and then when we have something to send, you can go ahead and call the send event with name method with the data you want to send. And here's how we listen for those events in JavaScript. Again, more boilerplate at the top, but once we have an emitter, we're able to listen to the events coming from native, like so. It's worth noting that this rather laborious system is the current situation, but I've watched a few talks and I understand that the React Native team are working on this area and it's subject to change in the future. It looks like they're moving toward a synchronous RPC style interface rather than this current set of APIs, so watch this space. Now, a problem that affects us building an SDK, but would also affect any React Native application that includes a non-trivial amount of native code. And this is the problem of answering the question, given a new feature or requirement, should you write your logic in native code or JavaScript? So let's take a look at the architecture of our React Native notifier. In essence, it's composed of our individual JavaScript, Android, and Cocoa notifiers, which are then customized for the platform and connected together. So at the top here is the encapsulating package, Bugsnag React Native. This contains Bugsnag core from our JavaScript notifier and some React Native specific JavaScript plugins, represented by these chunks alongside it. And these tailor it to the React Native JavaScript environment. Then we cross over the bridge over to Bugsnag Android on one side and Bugsnag Cocoa on the other to support both native platforms. And sitting on top of these is a thin bridging component that deals with connecting the two layers together. So that's using the techniques I explained in the last section, exposing a native module interface and sending events. For some features of our notifier, there were multiple places that we could feasibly have written the logic, and here are three of them. Delivering error reports and sessions to our API. This involves serializing a data structure to JSON and sending it in an HTTP request. Caching payloads on disk when the network is unavailable or the application is in a volatile or crashing state. And recording breadcrumbs. So these are collections of events leading up to an error, which we track to help reproduce the state that caused an error. So things like when the device changes orientation, when the user navigates to a different controller, or when the app is foregrounded or backgrounded. So let me take you through these features and describe where we put the logic and why. Both the JavaScript and native layers are capable of encoding JSON and sending HTTP requests. And in fact, since we already have the JavaScript and native notifiers that stand alone, this feature is implemented on them both already. We decided to centralize our delivery logic in the native layer and use the native delivery mechanism. And the primary reason for doing this is that if you're stuck in a crash loop before the JavaScript layer is starting, then the only chance you stand of sending a report is if the native layer sends it. Additionally, the JavaScript layer makes it easy to plug in a delivery mechanism which defers to the native layer for sending reports. And that hands off a plain JavaScript object representing an error report, which is perfect for serializing across the bridge. And we also want to co-locate our delivery logic with our caching and retry logic, which I'm about to talk about in a second. So the behavior of our native mobile notifiers is such that while the application is crashing, or while the device is offline, we opt to save the error report to disk before attempting to send it. And in the context of React Native, while it's crashing, it would be pretty wild for us to expect to be able to successfully serialize the error, pass it up to JavaScript over the bridge, and have it be serialized again via the React Native APIs that interact with the file system. The obvious choice then for this is to do it in the native layer, and so our logic around caching payloads and the strategy by which their sending is retried lives in the native layer, and that's co-located with the related functionality of sending payloads from the last slide. And lastly, in terms of breadcrumbs, we were on the fence about this one. Again, since both our native and JavaScript notifiers record breadcrumbs anyway, it's simple and straightforward to choose either layer for the user, app, and device events. However, when we looked at putting this in the JavaScript layer, there was a problem with one type of breadcrumb we record, and that's changes in connectivity, such as connecting or disconnecting from a Wi-Fi network. To do this in JavaScript, we needed to use a third-party dependency, a netinfo package, and this is something which actually used to be in React Native core, but which was removed and put into a third-party package. So the reason we ended up choosing native for all breadcrumbs was due to the complexity of going from 0 to 1 dependencies for something that could be done for free in the native layer. It made the build more complicated and more brittle, it reduced the range of React Native versions we could support, and was just more hassle than it was worth. So after choosing native for that one kind of breadcrumb, we chose native for all other breadcrumbs for consistency. So you might notice, like I did, that for each of these examples, our choice was to push it into the native layer. I don't know if this is specific for our problem set or more widely applicable to all React Native apps, but the pattern for us at least seems to be, if you have to think about it, then write it in native. The reason I think this might just be limited to us is that it seems related to the fact that we treat the native layer as the center or source of truth, and the JavaScript layer exists as a sort of satellite around it. I think if the JavaScript layer was treated as the source of truth, a lot of these decisions would be reversed. I would recommend modeling the data in your application, looking at how and where it needs to flow, and then choosing a source of truth. So a little bit of a zoom out from React Native specifically. When I set about rewriting our browser notifier in 2017, I wanted to future-proof it. At the time, it was a single humble JavaScript file, which was nice to an extent. But when considering multiple platforms, that wasn't very helpful for picking out and reusing the common parts. So at the time, as well as Bugsnag.js for the browser, we also had a completely separate notifier for Node, as well as some custom unique JavaScript in our React Native and Unity notifiers. As an artifact of a young business, these notifiers were written by different people at different times on a somewhat ad hoc basis. But this meant that we were solving the same problems on different platforms in up to 4 different ways. The interface was inconsistent if you as a customer wanted to integrate Bugsnag into more than one platform. And for us, the maintenance was a nightmare. I knew that the number of JavaScript-based platforms we were going to have to support was only going in one direction, so when embarking on the rewrite of our JavaScript notifiers, I wanted to ensure maximum code reuse. Fast forward back to today, this is how the JavaScript codebase is laid out. It's set up as a monorepo, which we manage with Learner. It's got many smaller packages. It's not a monolith, so it's modular, which means each part is easy to test, easy to comprehend, and easy to replace. So first we have Bugsnag core, and this contains the basic abstractions, utilities, and constructs that we would use to build a notifier on any conceivable platform. Then we have a bunch of modules that are prefixed with Bugsnag delivery. These are responsible for hooking into the platform's primitives for sending events and sessions. So in the browser, this is Ajax, and in Node, this is the built-in HTTP module. Then we have modules prefixed with Bugsnag plugin, quite a lot of them. And these plugins are responsible for injecting all of the platform-specific functionality that is not included in core. And then to create a notifier, we simply assemble the existing reusable components and create some more plugins to fill the gaps. So to illustrate, we have the top-level notifiers here, browser, Node, and Expo. And so you can see they contain core, their own delivery package, and then a collection of plugins that are relevant to the platform. So after these notifier rewrites, the Bugsnag.js repo now provides notifiers for browser.js, Node, and Expo, and it's become the base for our new React Native notifier, which we actually shipped this week. So what have the benefits been? Well, each new notifier we add requires less new code to bootstrap. Before, we would have to write everything from scratch, but now for each new platform we can assemble everything from Bugsnag core, some existing plugins, and be off to a good start before tailoring even a single line of code to the new platform. We have consistency between all JavaScript platforms out of the box, both in terms of API and functionality. And whether you're using Bugsnag in the browser, in Node, in Expo, or React Native, how you initialize, configure, and operate it is the same. We reuse all of Bugsnag core on all platforms, and we also get good reuse out of plugins too. So for example, we have a plugin that monitors network requests to leave as breadcrumbs. We wrote this module for the browser, but since React Native and Expo use the same window.fetch API, this plugin simply works as is for those platforms too. Equally, if we need to diverge or deviate slightly too much from an existing plugin, we're not tied to it. We simply plug out, write a new one, and plug that in instead. For everything in core, logic that was previously written in a variety of ways for each supported platform now has a canonical implementation that is heavily tested across a multitude of platforms, devices, and versions. If we detect a bug in this and fix it, that fix gets tested across the huge matrix of devices, and all the other platforms get the fix for free. So all in all, we've managed to get great JavaScript reuse across all of our platforms, including React Native, and I think you do that too. So to conclude, I don't have a prescriptive set of instructions on how to write software with React Native the right way, but what I would like you to take from this talk are the following reflections. React Native isn't a great abstraction. If you want that, use Expo. Otherwise, React Native's strength is that it allows you to share JavaScript components between native platforms, but without losing the flexibility and power of those native platforms. Communicating via the bridge is straightforward if you want to call native methods from JavaScript, but otherwise it's pretty tricky. The React Native team are working on making this better, but in the meantime, consider how you want your data to flow and design around established patterns rather than making life hard for yourself inadvertently. Deciding where functionality should live is an interesting problem due to the multi-tieredness of the platform, but you should find your source of truth, which sounds like a nice mantra to live life by in general, but then when you've found it, you should put most of your logic there. It's really rewarding to reuse JavaScript you've already written like we did, so make the most of that. And finally, as with any platform really, there are some interesting pitfalls. With React Native, its complexity just lends itself to there being a few more than usual. Be aware that sometimes it can be a very frustrating platform to work with, and give yourself more time to figure out strange bugs and behavior than you usually would. And that's all I have time for. I hope this has been interesting. If you have any questions, feel free to reach out on Twitter or email or the live chat. Otherwise, thanks for listening.